in, right, Vitor?
Should be.
And system is starting. You know, this was working so well. Here we go. Okay.
You messed it
You
up.
gotta
So-
update it.
You sold it.
Basically, what's happening is this. Pressure sensor is like my legs when I teach second grade, right?
Okay.
What it's measuring is collisions with the little ankle biters. So, no, it's a true story. So, the first thing you're going to do is you're going to look at the relationship between pressure and volume. So, you have a syringe, right? And what you're going to do is, over here on page 2, what you're going to do is you're going to start with a volume of 5 milliliters. So, take yonder syringe, push that down, you're at 5 milliliters. This is the size of the classroom. Screw that on, so we've set the size of the classroom. Now, basically you're going to look at 3 different things. You're going to look at the size of the classroom, you're going to look at the number of Timmies in the classroom, and you're going to look at how many Skittles Timmies have, okay? We're going to keep 2 of those constant, we're going to change the other one. So in this situation, we're not going to change the number of Skittles, okay? No new mothers are allowed in. We're not going to let energy flow out, we're not going to let energy flow in. So, you're going to hook this up, right now we're reading 96.52 kilopascals. So, within here there's a mechanism, and you have all these billions upon billions of little nitrogen and oxygen molecules, not air molecules, nitrogen and oxygen molecules, that are bouncing off this thing, and we have arbitrarily, as a society, said, we're going to call this kilopascals. And then we developed technology that says that's 96.57. Okay, there you go, there's your volume and your pressure. So then, you're going to take the size of the classroom, and you're going to change that, and you're going to pull that back to 7. Now, before you do that, what's going to happen to the pressure?
It's going to go down.
Why is it going to go down?
Volume increased.
Yeah.
So what? Physically, what is happening to make that pressure decrease? Just don't tell me
There's
the
more
volume's
room
gotten
for the
bigger.
oxygen and nitrogen particles to move around, so they don't hit it as
Yeah,
much.
there's less collisions.
There's less collisions, right? So I'm going to keep the same number of second graders, but I'm going to make the room bigger. So what's going to happen to the number of collisions with my ankles?
Go down.
They're going to go down.
Less bruises.
Okay? Less bruises. Okay? So as the volume is continuously getting bigger, we've taken the second grade classroom and we're going to make it bigger and bigger and bigger and bigger and bigger. Are we going to change the number of second graders?
No.
No. Are we going to change the Skittles that the kids have?
No,
No. So what's going to happen to the pressure?
it's decreased.
Decrease.
Pressure's going to go down. Okay? Dr. Botts, you remember your ideal gas laws?
What's that?
You remember your gas law equations?
No.
Okay. All right. Okay. All right.
No.
Taught them well.
So you're just going to keep pulling this further and further and further back, and you're just going to record those values. Okay? Got that one?
Yep.
Okay. Now, that's the easiest one. On the second one, over here, now, we're going to talk about puffs, and this is not in an illegal drug sense. Okay? What we're calling a puff is 3 milliliters of air, okay, which is going to contain a certain number of Timmies. So here's your technique on the second part. You're going to start with this thing at 3. That's a certain number of kids in the classroom, okay? We're going to call one puff 3 milliliters. You're going to get this set, and then you're going to screw this on, okay? Then, here's the next thing. This is where this gets a little bit more complicated. Then you need to pull that back till it reads 10 milliliters, okay? And then you're going to see what that pressure is reading with you have 3 puffs and a classroom of 10, okay? So visualize this. We have 3 kids in the classroom, and then we need to adjust the classroom so that it's at 10, okay? 3 kids, size of the classroom is 10, okay? You're going to get that reading. Then you're going to unscrew it. Then you're going to go to 6. Now we're going to have 2 puffs in the classroom, okay? We're going to screw this back on.
Pull back to 10.
Then we're going to pull it back to
10.
10. So that way we're keeping the size of the classroom the same. Then you're going to do that, unscrew it, go to 9. Now eventually you're going to end up here like at 15, okay? So when you go to 15, Yeah, then you actually have to then compress it down to 10. Okay? So some of these you're going to expand, some of these you're going to compress. So again, focus on what you're holding constant. Are you changing the Skittles that the kids have?
No.
No. You're changing the number of kids in the classroom, right? So as you're putting more and more kids in the same classroom, what's going to happen?
Pressure goes up.
Pressure should go up. So again, you have to focus on what you're holding constant and what you're changing. Okay? So those are the two relatively easy ones. Now, the third one, hand me a big test tube.
We're like Nick Cannon.
Where'd the test tube go?
It's on.
Oh, it's on the ground. No, I'm playing. I have no idea.
Oh, it's shattered all
Where did it go?
How did we lose the test
I
tube?
think-
the jacket.
I think you picked it
over.
up.
Someone grabbed it. You grabbed it from over here, I'm pretty sure.
Yeah, there's no.
Did you put it-
because I didn't touch it.
I didn't hear a crash.
I didn't hear.
Oh,
It's fine. Oh, yep.
Okay.
I knew it.
Now, so on the first ones, you need to have this where the syringe is screwed directly to the pressure sensor. On the next one, you need to change it up, where you're going to have this tube, which is going to be screwed to the pressure sensor.
Ooh, we're doing chemical reactions.
No.
Oh,
Homemade.
Now, with this one, here's what we're going to do. We're going to change the temperature. So what you need to do first, when you first get back there, I got big beakers. You need to fill those beakers up so that when you submerge this test tube in it, it basically kind of goes all the way to the top. You want to be able to completely submerge this test tube. Get that on a hot water plate. Get that heating up first, okay? Because it's going to take a while to heat up that much water. So before you start anything else, the first thing you do is grab a hot plate and get that water heating up. Then, you're going to measure the temperature in Kelvin. So what we're going to do is we're going to start warm, and then we're going to cool it down. So don't necessarily boil it. Maybe get it up to 70, 80 degrees Celsius. So let that temperature stabilize, and you might have to, like, once it gets to a certain point, you might, like, turn down the heating element so that you kind of maintain the temperature. So you want to have this in there, because what you want to allow what you want to do is allow that thermal energy from the water to seep across this barrier and give energy to the nitrogen and oxygen molecules that are inside of there. So this is why you kind of have to let it stabilize for a while. So you're going to have this. This is going to go in here like this, okay? The first thing you're going to do is you're going to have the warmest temperature. So get that water, and I've got temperature probes that you're going to plug into here, okay? So you're going to actually be running two probes on here, temperature and pressure. Measure the temperature of the water. Now, you want to make sure that the bottom of that temperature gauge is not resting on the bottom of the flask, because then you're measuring the temperature of the bottom of the flask. You want to measure the temperature that's inside of that. And you might even kind of want to stir that every once in a while to make sure that everything is well mixed. So, you're going to get a warm temperature. Let it stabilize. 70, 80 degrees, something like that. I'm going to have a bunch of ice. Then, you're going to take ice, and you're going to begin to add that to the water. So, set off the temperature, set it off the hot plate, or turn off the hot plate. Guys, we don't want to try and warm it up and have the hot plate on at the same time. It's like driving with the gas pedal and the brake on at the same time. So you're going to add some ice. Drop that temperature 10 or 15 degrees. Okay? Let it stabilize. Get a new temperature. Add some more ice. Now, what you might have to do, because you're going to be adding ice, you're going to be adding fluid to it, if that water level starts to overflow, grab a smaller beaker, bucket out some of the water so that you're not overflowing the beaker. Okay? So then, again, you're going to get 10 or 15 points along here. You're going to say, okay, hey, here's the temperature, drop that down, measure that Pascal. So this is the only time you're going to be changing the number of Skittles that the kids have. So are we adding Skittles or taking away Skittles?
Adding. Taking away.
Initially, we're going to add them, but then the next step is
Take them away.
we're going to take them away, right?
Amen.
Give me your
Are you going to change the size of the classroom?
No.
No. Are you going to change the number of kids in the classroom?
No.
No. So keep that in mind. Okay? All right, let's go get data.
Let's go daytime.
See the god of football.
All right.
Of course they're gonna say that.
So here's what we talked about, and this is going to be the basis of the lab today. So you have pressure, and you can have
Lab day.
isothermal,
Hot.
you can have isobaric, you can have isovolumetric. Okay? So all three have something that you're going to hold constant. So if you're isothermal, what does delta T equal? 0. Okay? Now that starts a whole cascade of ramifications. So if delta T equals 0, delta U is going to equal
0.
0 because delta U equals 3/2 NR
Change
Delta
it.
T.
delta T. So if delta T is 0. Now, we're not saying, listen to me, I'm not saying there's not a temperature. I'm just saying there's no change in temperature. Okay? That's not what we're saying. It's like if Louis comes in and he says, hey, Mr. Burkamp, I didn't find any money today walking into school. Bummer, Louis. Okay? That doesn't mean Louis doesn't have money. He's at his account just
What are you
Me
doing?
too. What are you doing?
What is
It's
this?
not an alcohol.
Is that a
Oh no, I was just like seeing if it was. Why is this loose?
Vito.
because it's
Why is
my
it? Why
stuff.
wouldn't it be
Why are
attached?
you
Wait, what
messing
is
with
it?
it?
Oh my gosh, you almost broke it.
Give me it.
Put it
Give
up
me.
there.
Put it over there.
I'll take it.
No, I need it. Just keep
Bring-
working.
No.
No, that's a terrible idea.
No, that's fine as long as
I'm gonna put it like this. Know how to.
Why'd you turn it off?
We don't know what to do with it. Give us some.
there.
Valid.
Yeah.
Okay. You know why I don't teach freshmen?
Because
Because I got.
they keep touching
Yeah.
stuff.
Vito, you're being a freshman right now.
Hey.
Okay.
Freshman behavior.
So delta U equals two things. Now here's the anomaly about delta U. Delta U is one of the most important concepts in all thermodynamics, but we can never measure it directly. So if you look at the probes that we can buy for LabQuest, we can measure temperature, we can measure pressure, we can measure volume, okay? We can't directly measure delta U because it's the sum total of all the energies that exist. Now here's what's important. This is delta U. This isn't the value of U. This is how much delta U is going to change. So if delta T equals 0, all we're saying is that we're not going to change the sum total of all the energies. I'm not saying there aren't energies. I'm just saying we're not going to change them. Okay? Now, delta U also equals Q plus W. Okay?
W.
So if delta U equals 0, that means Q has to be and W have to be
Equal and
Equal
opposite.
If Q is positive, energy is flowing into the system. If Q is negative, energy is flowing out of the system.
Yep.
If work is positive, volume is getting smaller. If work is negative, volume is getting bigger. Okay? Now, there's two ways you can calculate work, depending upon the situation. If it's isothermal, because of the fact that you're trying to find the area underneath the curved line, this is the only time we will ever use calculus, because we're finding the area underneath the curved line. And that's nRT natural log VI over VF.
I can't see
Right?
them all.
That's the only time you're ever going to use natural logs. And the only time we're really going to use calculus, because all the other times we've had nice little triangles and constant slopes and things like that. So here's the ramifications of this. If your volume initial is less than your final, okay? Volume final is bigger than your initial, however you want to view it. You're going to be taking the natural log of a value less than 1. If you take the natural log of a value less than 1, what's the sign of that value?
It's negative.
Negative.
Negative. So that's why if the volume is getting bigger, work is negative value. Because what's happening is that it's costing the system energy, okay? Because you got to work against trying to keep this thing down. So delta U is going to equal 0. That means your Q and your W are going to be equal and opposite. So if you can measure the work, automatically you're going to know your Q value. You just change the sign of it.
Can you quickly go over the on the system versus from the system?
Okay,
That
so
was kind of
thermodynamics is all about prepositions. So let's say, for example, I take this syringe, okay, and I compress it.
yeah.
So on that situation, I'm doing work on the system
Yeah.
because I am compressing that. And if I take this syringe, okay, and I push that down, first off, what's happening to the volume? Is it increasing? or
Decreasing.
Decreasing.
So I'm decreasing the volume, right? So I'm doing work on the system. So this is work on the system,
So that's
okay?
positive.
Because it's,
Positive work.
Because the volume is getting smaller,
Uh-huh.
okay?
Ln.
Now, if I put this into a container like a hot water bath, and it begins to take in thermal energy, and that syringe begins to move, then that would be work being done by the system.
Negative work.
Because it's making the volume get bigger, so it's costing it energy. So that's why when you put your hand in front of your mouth and you pucker and you blow, it feels cool. Because what's happening is that gas, as it exits your mouth, expands. And it has to push against the atmospheric pressure that's trying to keep it contained. So that's why when you do that, it feels cool, because it's costing it energy. Because that is work being done by the system against the atmospheric pressure that's trying to keep it contained. Okay?
yeah.
So on the system, by the system. Then you can talk about energy flowing into the system. So if energy is flowing into the system, you have a positive Q. And if energy is flowing out of the system, you're going to have a negative Q.
Okay, so if
What
it's so they're inverse, Q and W are inverse.
No. They have nothing to do with each other. Nothing to do with each other. You could have positive Q and
Positive or
W. I could have both negatives. I could have one positive, one negative. The only time they're inverses of each other
Thermodynamics.
is when delta U equals 0.
Gotcha.
Okay? That's the only time they're inverses of each other. Yes.
So what is Q? What's the difference between Q and U?
Okay. Delta U is the sum total of the energy that's already in the system. Okay? So right now, that has a certain amount of internal energy. Okay? I can put a temperature probe in that I can measure it. Okay? Certain amount of energy. So what delta U represents is, and I can't measure delta U directly.
Yeah.
Can't measure. I have no probes to hook onto that thing to measure delta U. But what I can do is I can, like for example in the lab, you're going to measure the temperature of the water that the test tube is immersed in. So if I can measure the temperature of the water, by default then I'm measuring the kinetic energy of the particles inside that container. So I don't know what the value of delta U itself is. So like if I can measure the change in temperature of the gas inside of it,
You find delta U.
then I can find delta U.
Okay.
So that's why I said, so we macroscopically measure temperature and volume. We use that to infer delta U.
Yeah. And
Okay.
so Q is just the energy moving.
And you could calculate that using, just like we did, MC sub P delta T. So you could actually calculate Q. If you know like the mass of the gas in here, and you know the change in temperature, and if you know the specific heat of the gas inside of here, and you know, I could figure out how much energy was actually put in
Okay.
by measuring those values.
Or how much is taken out.
Exactly.
Okay. Nice.
When would delta U not be 0?
So let's say, for example, when you have a isobaric expansion, okay?
Okay.
So if you have an isobaric expansion, right? If you go across like this, what's happening, by definition, what's happening to your pressure?
Increasing. No, staying the same.
Same. So I'm keeping the same pressure. I got NR, but what's happening to the volume?
It's increasing.
It's increasing. So I'm increasing my volume. So what's the only way that, if PV equals nRT, If I'm increasing my volume and my N and my R are staying the same, what has to happen to the temperature?
Temperature has to increase.
Here I am increasing my temperature. So as I go across, I'm increasing temperature. Now, delta U is going to equal Q plus W. True?
Yeah.
Okay? Now, here's the deal. And delta U equals 3/2
And
NR delta T. True?
Yes.
So as I go across, what's the sign of my delta T?
positive.
Positive. Okay, so I've got a positive delta U. Start with that idea.
Okay.
Now, because my volume is getting bigger and it's a horizontal line, my work is going to equal negative P delta V. It's a rectangle. Negative sign is out there to make the sign conventions work. Volume is getting bigger. So what's going to be the sign of my delta V?
Positive.
Positive. So I'm going to have a positive delta V multiplied by a negative pressure, so I'm going to have a negative work. So my work here going across is going to be negative. Cool with this?
Yeah.
Cool with that?
Yep.
Literally. But my delta U is going to be a,
Positive value.
because I have an increase in temperature. But delta U also equals Q plus W. So what has to be the sign of my Q?
Positive.
Positive.
It has to be a positive value, but it has to be bigger or smaller than the work.
Bigger.
Bigger.
Yeah.
That's the only way that I can end up with a positive delta U. So if I go across like that, I've got a positive delta U, I've got a negative W, and I'm going to have a positive Q, which has to be bigger than the work. So this, in terms of like my last will and testament, this would be a situation, I'm going to leave Jackson $5,000. He has to spend $2,000 of it doing work. He gets to keep $3,000. So the $3,000 would be his delta U value. The $5,000 would be the Q. The work that he has to do would be the negative $2,000. Okay?
Okay.
So what this would look like, if I said, hey, I want you to do this. You want a positive Q. Are you going to put it in an ice bath or are you going to put it in a hot water bath?
You're gonna put it in hot water.
Hot water.
Why?
Because then it'll
Temperature.
take energy hot to cold.
Energy is flowing into it, right? Energy is flowing in. Cool. Energy is flowing in.
Yeah.
But what would you see happening to the syringe?
Increase.
It would expand. So
So work is being done.
I can't do this with a sealed system. It has to have, the volume has to have the capacity to change. And I want a membrane that will allow that energy to flow across. Okay? Good with that.
Yep.
If I reverse it, what would happen?
Q would be negative.
Q would be negative, so I would put that in an ice bath. Okay? Put that in an ice bath. Energy is going to flow out. Volume would get smaller. Delta U would be a negative value. Good with that one.
Yep.
Yeah.
Okay, now, what we really haven't talked about is isovolumetric. So on a pressure volume graph, if you have an isovolumetric line, so let's say we're going to go from here down to here. What's going to stay the same?
No.
Volume.
Volume.
Volume's going to stay the same. NR, right? But if I go down like this, what's going to happen to my pressure?
Decrease.
It's going to become smaller. So to balance this, what has to happen to the temperature?
Big T. Oh, smaller, yeah, small T.
I got to have a smaller temperature. So to make this happen, would I put it in an ice bath or a hot water bath?
Ice bath.
Ice bath. In an ice bath, I'm going to have energy flowing out of this. Now, here's the interesting thing. Delta U equals Q plus
Forgot the U.
W. There's a U in there. Okay? Trust me.
Gotta look over.
It's jacked up, but it's there.
It's like Connor's work.
What's the work?
Wow.
Work is negative.
Nope.
Oh,
No.
There is no work.
Oh.
Why?
Because it's a vertical line.
There's no change in volume. It's a vertical line. There's no area. So what this means is that delta U equals Q.
Q.
So this one would be a situation, and that's why the part of the lab, you're going to have a fixed graduated, you're going to have a fixed test tube. You're going to have a fixed volume. So part of the lab you're gonna do with the syringe where you can change the volume. Part of the lab you're gonna do where it's gonna be locked in place and you can't change the volume, okay? So anytime you can't change the volume, guess what? That's gonna be ISO.
Volumetric.
If you can change the volume, it could be one of the other ones, okay? All right? Got the idea? So if this temperature drops, if I go down like this, I'm gonna decrease the temperature, right? Which means what's gonna be the sign of delta U?
It's gonna be negative.
It's gonna be a negative delta U, because work is gonna equal
It's
0. Got that? Okay. Anybody have any questions on that assignment from yesterday?
I have one. It's a little question. So like on
So I'll just give you a little answer.
on 1B,
On
so if
1B,
instead of can you round up? Like so if it's a number of times that you're raising something up, can you round up?
yeah. So that answer, like on 1B, should be between 2 and 300.
Wait, which one?
like cause it was above 5. I rounded down because you didn't get a full like.
No,
deal.
round up.
Okay, round up.
Round up.
Well, I was thinking of the old school bus thing. If you had like 5 school buses,
On number 8,
kind of half a school bus.
you should have 5 separate calculations. You warm the ice, you melt the ice, you warm the water, you boil the water, you warm the steam. So that sum total, and make sure that I see each one of those, okay? Your sum total on number 8 should be something times 10 to the 6th joules.
And what does on number 17? What does that graph look like?
On 17?
Yeah.
I don't know. I'll just wait. What do you want it to look like? A squirrel?
Yeah.
Okay,
That's what I drew.
Make it look like a squirrel.
so what do you want to do first?
You do
Oh no.
An isobaric
constant pressure. So
compression or expansion? What's this?
compression.
I don't know. Ask what it's doing.
Compression.
So that's going to be like this. I'm going to compress it.
Yeah. So like that.
So it's going to be a horizontal line,
Yep.
like this.
And then isothermically back to its original volume. So that would be like that. Okay. Yeah.
That's it.
That's crazy.
That's what I thought.
Which one's going to take more work? The isobaric or the isothermal?
Barrett.
Why?
Area underneath it's larger.
Yeah. Now, here's an interesting idea. You have 2 isothermal expansions. One's at a higher temperature, one's at a lower temperature. Which one requires more work, or is it the same? So this is a higher temperature one.
Higher
This is lower
temperature.
temperature.
The higher temperature.
Higher temperature.
Why?
More area underneath.
More area underneath. So
Wow.
the higher temperature isothermal expansions or compressions take more work than
But why?
lower temperature ones.
Why?
What do you mean?
Like I understand that it's got more energy, but like why? Because it has more.
nRT, natural log of VI over VF. Mathematically, this is why the work is bigger, because the N and the R are the same. The change in the volumes are the same.
Yeah.
The temperature is higher.
Like conceptually, why?
Conceptually, because you have more energy within the system, so the particles are moving around more, okay? And so it has more energy, and work is basically a measure of energy. And so with more energy, that's gonna take more work.
Okay, I got you.
Yeah. Okay. Anyway. Your answer to 16A should be something times 10 to the 5th. And your answer to 16B should be something times 10 to the 6th.
Oh, let's check them. 18.
Your answer to 2 should be to the 4th. Your answer to 3 should be to the 5th. Both of your answers on 5 and 6, excuse me, the sum of your answers to 5 and 6 should be around 100.
And that doesn't matter, right? Whether it's Celsius or Kelvin.
Yeah.
Cause it's
No, because it's changing
change.
temperature.
Yeah.
Yeah. Okay, we're good. Going. Let's go and try sodium.
The sum.
Wait, if it's changed, do we have to put units on it still? Or can we just
That's a
put
good
like-
question.
Degrees?
Could you
Or
put?
do we have to
Usually
put-
you want to put something, whether it's
Yeah.
Kelvin or Celsius.
Okay.
Well,
Fair enough.
That's a great question.